In this video, we provide an introduction to liquids. Liquids have very many interesting properties. For one, we have said that they are the only state of matter in which the substance conforms to the shape of the container, but it does not occupy the entirety of the volume of the container. Liquids tend to be highly incompressible. That means that if you apply quite a bit of pressure, the liquid's volume won't change by much. Okay? And there are other interesting properties that we're going to try to discuss in this video. The first one is what we call surface tension. Okay, so that's the first thing that we're going to be talking about here. And that is what happens when you have a liquid in which there is an interface with another medium. Right? If you think about the molecules in the bulk of this liquid, what you have is that each molecule is surrounded by neighbors. But when you look at the molecules right at the surface, what happens is that they have an incomplete shell of neighbors. Right? So what that means is that those molecules at the surface are being pulled in by the molecules of the bulk, but not pulled in by anybody out here, because if this is an air-water interface or air-liquid interface, there's no neighbors to pull those molecules, to establish interactions with those molecules. Right? So this unevenness of interactions causes something that we call a surface tension, and that's something that can be measured. Okay, so it's pretty obvious that molecules that have, or liquids in which the molecules have very strong intermolecular interactions are going to have much larger surface tension than those liquids that are made with molecules or particles that have very small intermolecular interactions. Okay, so for example, water is one of the liquids that has a pretty large surface tension. Now there are other properties that we can examine related to surface tension when we bring a little bit of a liquid in contact with a different surface. Okay, so for example, suppose that we have here a surface of wax, and we're going to bring here a water droplet. Okay, so that is water. Well, so what happens here is that there's two forces at play. Okay, the forces that are acting within the water droplet is what we call cohesion. And much as with surface tension, the larger the intermolecular forces between the liquid particles, the larger the cohesion force. Now, we also have this different type of interaction, which is between the molecules of the droplet of the liquid and the molecules of the surface. And this is what we call adhesion. Right? So what happens in this particular case is that the cohesion forces, the interactions between water molecules and water molecules, are larger than the adhesion forces, the interaction of the water molecules with the wax molecules. Right? And what that means is that, well, this, due to surface tension, this water droplet tends to minimize the exposure to the wax, and that's what you have that this droplet beats up. Okay? What we say here is that this has a very high contact angle. If you measure that angle, that is what we call the contact angle, that will be pretty high. Okay? On the flip side, you can bring this to a surface that has groups here that interact favorably with water. Okay? For example, glass has a lot of OH groups on the surfaces, and those can establish hydrogen bonds with water molecules. So when you bring a water droplet right here, what will happen is that that water won't beat up anymore. And the reason is that the cohesion forces are now not so different from the adhesion forces. Now they are much more similar, and then you get this type of phenomenon where the water droplet wets that surface. Now this type of phenomenon can actually be exploited when you have very narrow glass tubes, for example. You have something like this, okay, and fill this, this is glass, and then you fill it with water. You're going to have a similar example to this. The water will tend to wet those glass walls, and then what you have is the appearance here of a meniscus, which is again a kind of response to the balance between cohesion forces between the water molecules and adhesion forces between the water molecules and the glass. Okay, so for in capillary action, what happens is that you can observe the liquid ascend through a column because again, these adhesion forces tend to be quite high in glass and water. Again, glass is generally terminated with OH groups, which attract quite strongly water molecules, given the capillary action effect. Okay? One more property of liquids that we're going to be studying, aside from surface tension, then cohesion, adhesion, capillary action, is going to be viscosity. We define viscosity as the resistance of a liquid to flow. Okay, and of course you can see how viscosity should also be connected to the intermolecular forces acting between the molecules of the liquid, right? So if the molecules of the liquid are interacting very strongly, then there will be a larger resistance to flow of this liquid, giving rise to a large viscosity. However, if those molecules or particles of the liquid are interacting not very strongly, then the viscosity will be much lower. Right, so this video has provided a very succinct introduction to interesting properties of liquids, and you can see how surface tension, cohesion, adhesion, and viscosity, all those properties are ultimately related to the intermolecular forces acting between those molecules in the liquid.